Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. Well, today's topic was suggested by a viewer, and I always love that when that happens. Mark from Process Solutions suggested the following topic: build an analog totalizer with the Horner OCS. Again, I always love it when we get suggestions from viewers for topics, not only because it gives me something to really dig my teeth into, but because I know that if one viewer is interested, certainly there's going to be plenty that are interested. Okay, so let's dive into our topic on analog totalizers, and here's how we're breaking down today's topic. We'll start with reviewing what is an analog totalizer and when is it used. There's some key design considerations. You need to, in order to do it well, you're going to have to measure accurately elapsed time as well as have accurate analog readings. We're going to show you, or we're going to talk about how we may need to design the logic to do analog totalizing in the OCS. And I've already created a user-defined function block that I'll show you at the end that if you want to use for a future analog totalizer application, you'll be able just to plug it right in. Let's get started. What is an analog totalizer? Well, basically, an analog totalizer is an electronic device that's typically used in conjunction with an analog flow meter or maybe an analog flow transmitter. And it's effectively used to totalize how much flow is coming out of that particular sensor. So for instance, if you've got a flow transmitter whose output is scaled in gallons per minute, then your totalizer is going to indicate the total number of gallons of flow. Now, many of you may already be familiar with a pulse totalizer, and that's probably a little bit more common application. So a pulse totalizer would be an alternative to an analog totalizer. Effectively, it's a counter that has the ability to scale the input. For instance, you might have a scenario where you have a flow transmitter, but instead of that flow transmitter putting out an analog signal, it may put out a pulse train or a certain number of pulses per gallon of flow, for instance. Pulse totalizers, by their very nature, are quite a bit easier to apply than an analog totalizer because really all they have to do is count up the pulses and multiply by the scaling factor, and you're pretty much done. But today we're going to go through analog totalizing because it is more of an effort, although it's still very attainable in terms of doing that with an OCS. Why do we want to do analog totalizing with an OCS? Well, there's a few reasons. First of all, if you eliminate the need for a separate instrument to totalize your flow, now by having that function built into the OCS, you can take advantage not only of calculating flow, but also utilize the logic control capability, the data logging capability in the OCS, alarming in case your flow goes below a certain level or above a certain level. You can also get your totalizer onto an industrial communication network like Ethernet IP or Modbus TCP. Lots of good reasons to want to do the totalizing in the Horner OCS itself instead of having a separate instrument. Now let's start by talking about how totalizers work, or analog totalizers work. So if we take a look at that chart on the right there, I've graphed flow rate on the y-axis and time on the x-axis, and you can see the blue curved line there that indicates flow, and effectively that's flow rate versus time. Our job, if we're an analog totalizer, is effectively to calculate the area under the curve, and that gives us our total flow. Now, how can we do that effectively? Well, the easiest way to do that is for us to take periodic analog samples, that would be our flow rate samples, and effectively create a slice that we can then calculate the area of, and to get the total area under the curve, we just take the area of each individual slice and we sum them up, and now we have our total flow. So it's really fairly straightforward. Now, in terms of the area calculation, the area of that slice that we're going to be dealing with, you can see that's effectively a trapezoid. So to calculate the area of a trapezoid, it's as simple as taking our average flow over the start and end of that sample times the sample time, or the amount of elapsed time in that sample, and that will give us the area under the curve for that slice. The basic function of our OCS-based analog totalizer is as follows. We're going to measure an analog signal from a flow meter. Maybe it represents gallons per minute when you're talking about engineering units. We're going to measure the incremental time between analog samples. And we're going to want to do that with a fair amount of resolution because we want to have an accurate result. We don't want to miss any of the details there. We're going to calculate our incremental flow just by doing the math for the area under the curve of that individual slice. And then we're going to sum up our incremental flows, our individual slices, to create our total flow. So that's really what we're looking at here. Pretty straightforward. Now, which OCS should we consider for doing analog totalizing? Well, frankly, just about any OCS could be an effective analog totalizer. It really depends on your application, how critical it is that you get the utmost accuracy of your flow. For instance, if you're measuring the flow of a coolant or something like that, and you're not really needing incredible resolution and perfect accuracy, then just about any OCS will work just fine. But if you're looking to do it the best way possible, I would recommend that starting with the analog signal, you're going to want an analog signal that updates each scan, and you're going to want an analog signal that has sufficient resolution and accuracy for your application. So again, the more demanding the application, the higher quality or the higher specifications you should be looking for from an analog standpoint. Now, when it comes to measuring incremental time, that's the other part of the equation, pretty much all OCS models have similar capabilities for measuring incremental time. So that's not as big of a factor, although there is some advantages for picking an OCS model that may have a slightly faster scan time. That can be an advantage in certain situations. So for the purposes of our example today, I would probably recommend, let's say, an XL4 with Model 5 built-in I/O. Why would I recommend the Model 5 built-in I/O? Well, because the analog I/O is built in, the analog conversions or the analog samples that we're going to be taking of our flow meter are going to be happening every single scan. And that's going to keep our analog samples synchronized with our scan rate. That's going to help with our accuracy there. Also, the Model 5 built-in I/O has 14-bit resolution, which is really nice resolution. And the XL4 and the XL4 Prime both have a pretty fast scan rate. So that's another advantage there as well. But that being said, plenty of other OCS models would work well. If you've got an application where, again, your accuracy isn't hypercritical, then a micro OCS with its 12 built-in analog I/O would be fine. So let's get back to the task at hand, and that is effectively taking analog samples, keeping track of our time, and calculating the area under the curve so that we get our total flow. So here's what we're going to do on each scan in our application. First thing we're going to do is we're going to calculate scan time. So how long has it been since the top of the previous scan? Why is that important? Well, we actually take our analog samples from our flow meter at the top of every scan. So we need to know how long it's been since the previous scan. So that's the first thing we're going to do, and that is we're going to calculate our scan time. The next thing we're going to do is we're going to take a look at our current reading from our flow meter, compare that against the previous reading from the flow meter, and using those two values, we're going to calculate the average flow rate over the past scan. That's important for calculating our area under the curve. Then we're going to calculate that area under the curve with simple mathematics, and that's our incremental flow. And then once we've calculated the incremental flow for this particular scan, we're going to add it to an accumulator that's going to give us our total scan as we go. Again, pretty straightforward. Some of you may ask or may be thinking, hey, wouldn't it be easier instead of calculating scan rate and those sorts of things? Most of you know that there's a 10 millisecond, 100 millisecond, and 1 second tick available in Cscape when you're configuring your OCS or when you're programming your program. Why not use that? Well, effectively, with that particular tick, there can be some variations based on scan rate. In most applications, that's not a big deal. But in an application where you're trying to accurately calculate volume, those little bit of inaccuracies can make a difference over time. So in our application today, we're not going to use the ticks as our indicator of time. Instead, we're going to calculate scan rate of every particular scan. How are we going to actually do that? Because I think calculating scan rate on a real-time basis is not something most of us do in most applications. Well, to do that, we're going to need a fairly accurate time source, a really accurate time source, frankly. And the most accurate time source available in the OCS is a 10 megahertz clock that's built in to the OCS high-speed counter capability. So we're going to take advantage of that built-in 10 megahertz clock. So what you can do is you can go into the high-speed counter configuration, and even if you're not doing any high-speed counting in your application, you can configure the high-speed counter to have a totalizer using the internal 10 megahertz clock. And then what you're going to end up having is an analog input register that's double integer in size that's going to be continuously incrementing in 0.1 microsecond increments. And by comparing the value in that accumulator between scans, you can very accurately determine what the elapsed time has been since the last scan. Generally, that calculation of time is very easy, right? We take a look at that accumulator this scan, we compare it with the accumulator last scan, and we just subtract the two. And that generally gives us our elapsed time in tenth of a microsecond increments. However, we have to look out for the situation where that totalizer, or that accumulator, I should say, has rolled over, because it goes up to a very large value, and then it eventually will roll over. So the way we can tell if it's rolled over or not is just by checking to see if our current reading is greater than our previous reading. If it is, we do the simple subtraction. If it's not, we have to do a little bit more of an involved calculation, but that's pretty straightforward, and I've shown it there on the right. Now that we've calculated our elapsed time, the next thing we need to do is we need to calculate our average flow rate. Again, simple mathematics. We take a look at our analog reading this scan, we add it to the analog reading of the previous scan, divide by 2, and that's our average flow rate. Calculating the incremental flow is just the area under the curve of that trapezoid, which is our average flow rate that we just calculated, times the scan time that we calculated earlier, and that gives us our incremental flow, or the amount of volume of fluid that we have incremented over the past scan. So next it's just a matter of adding the incremental flow to an accumulator and keeping track of our total flow. That's really what's involved in our application. That's the logic we're going to need to create. So what I have done is I have actually already coded this in a Cscape program, variable-based Cscape program, and I'm going to review that with you now. So here's my program. We're going to kind of walk from top to bottom, and I'll show you what we've done here. First of all, it does require that we configure the high-speed counter. So let me go ahead and go to the hardware configuration. I will go under local I/O. In my example here, I've used a Model 2 because that's what I had in the lab. But again, if you have an application where you're looking to do this as a primary part of the application, the Model 5 might be a little bit better choice. Gives you a little bit more analog resolution. But anyway, I'm going to go to configuration and then module setup. And then under digital inputs and high-speed counter, I'm going to make sure I set one of the counters to totalizer with the internal mode of the internal clock 10 megahertz. So by configuring it in this fashion, and I don't have to configure anything else at all, I know that I have a analog input register that'll be a double integer register that will be sitting there continuously incrementing that I can use to compare and calculate elapsed time. Piece of cake. So that's the configuration requirement for this example. So let's walk through the logic. So I start out by effectively taking a look at the current reading in the high-speed counter accumulator. Again, that's counting all the way up at a 10 megahertz rate. And then I'm also storing away for use on this scan the analog input value from my flow meter. And I'm calling this analog input now. And one thing you'll notice is that when it comes to the analog reading, I'm immediately converting it from an integer to a long reel. Now, what's a long reel? A long reel is a double precision floating point value. The reason I'm doing that is when you're calculating flow, you don't want to have any round off errors. So I'm using the highest precision math that I can, again, primarily to eliminate the round off errors as we're calculating our incremental flow and then eventually calculating our total flow. So I'm using primarily long reel math in this particular exercise. Now that we've taken a look at our current readings of time and analog, now we're going to calculate our elapsed time. So when we calculate our elapsed time, again, normally it's a simple subtraction. What was the time now versus the time previously? And we subtract it. However, we have to check and see if there's been a rollover or not. That's what this less than instruction is doing. So if there's a rollover, a flag will turn on. If the rollover has not occurred, we do our simple subtraction. If the rollover has occurred, then we need to do a calculation that's a little bit more involved. Effectively, what we're going to do is we're going to take the previous reading that we had, subtract it from the maximum value that the accumulator can accrue, and then take that difference and add it to our current reading. And then that'll give us our incremental scan rate, if you will. Again, two ways of doing that, either a simple subtraction or a slightly more involved equation, depending on if we've rolled over or not. Once we've calculated elapsed time, then it's a matter of calculating our average analog reading. Again, very straightforward. We're going to take the reading from the previous scan plus the reading of the current scan, divide that by 2, and it's going to give us our average reading. Now, the next thing I'm going to do here is something that I'm choosing to do to make scaling easier for multiple applications. And it's also going to make it easier when I take this code and turn it into a user-defined function block. So what am I doing here? Well, effectively what I'm doing is I'm allowing as an input to the application for my application program to specify what is the minimum value of my analog input, what is the maximum value of my analog input, and these are in counts. So with a typical OCS analog input, let's say 4 to 20 milliamps, if you've got it configured for 4 to 20 milliamps, your minimum analog input value is going to be 0, and your maximum is going to be 32,000. So what I'm doing here is I'm performing some scaling. So I take my analog input value that's scaled from 0 to 32,000 and that average reading that I've just calculated up here, and then I scale that to between 0 and 1 to create what I'm calling a unit volume. Now, why am I doing that? Well, I might have an application where full scale for that flow meter is 100 or 1,000 gallons per minute, or it might be 0.1 gallons per minute, or it might be in liters per second or something. So by scaling my readings in a unit fashion, it's going to make it easier to scale it later to engineering units. So that's what I've decided to do here. Once we've got elapsed time and we've got average analog reading, then we multiply those two together and we get a result of the area under the curve. Now, the one thing we do have to look out for here is to make sure our units all match. And when we're talking about the units of time that are coming from that accumulator register in the high-speed counter, that is coming back in terms of 10 million counts per second. So if we want to get our volume in gallons per minute, for instance, we're going to have to get from 1/10 of a microsecond increments to seconds, and then we're going to have to get from seconds to minutes. So that's what I'm doing here. I'm dividing it by 10 million to get to seconds and dividing it by 60 to get to minutes. And again, everything's in long real math here. Next, I'm going to do one other thing, and that is I'm going to make sure that the value I just calculated is not negative, because we never want to have negative flow. How would you get negative flow? Well, remember, we're talking about an analog input here that is going from 4 to 20 milliamps. So it's going to be scaled from 0 to 32,000 when it comes into the OCS. Well, it's always possible that value could go slightly below 4 milliamps, and it could be slightly negative. And then we would be sitting there subtracting off flow, which we should never do. So all we do here in this one rung is just make sure that we never end up with a negative result from our calculation so that we don't have any undesired errors. And then finally, what we're going to do here is we're just going to sum up, okay, the total volume, basically by taking the area calculation we just made of our time slice and adding it to an accumulator of all the previous ones. All right, we also provide a means to clear our accumulator out. And then the last thing that we do is we scale our unit accumulator, which remember is still scaled from 0 to 1. We scale that to engineering units, minimum and maximum. So the minimum might be 0 gallons per minute. The max might be 1,000 gallons per minute. So then we take our accumulator and scale it to engineering units. And finally, at the end of the scan, there's a little housekeeping we have to do. We have to store away our current time reading from our high-speed counter and our current analog reading from our analog input, because that's what we're going to compare against at the top of the next scan. So that's what's involved in doing analog totalizing with an OCS. And some of you are thinking, boy, that sure looks complicated. It's really not that bad. Let's take a look at the bench. I've got an example here that I will show you on the bench. What I have here is what I'm showing on the screen is my scan time calculation. I'm showing my flow, which is coming in from a flow meter that I'm simulating with an analog input here. And then currently, my totalizer is not enabled because in theory, I don't have any flow going on right now. This little 120 counts or whatever is just noise at the very bottom. Now I'm going to go to another screen where I'm showing my engineering unit scaling. So from 0 to 32,000 counts on my analog input, I'm saying that correlates to 0 to 10 gallons per minute. All right, so let's go ahead and enable totalizing. Let's get the flow moving here. And you can see that my flow average, this is just a calculation I've made on my average flow based on my analog input value. Let's say it's right around 5 gallons per minute. And my total flow accumulator is sitting there just moving up and totalizing and counting up the total gallons of water, let's say, in my application. Very good. So that's really what's involved in terms of doing analog totalizing with an OCS. The next thing I think we should do is I should show you how we could take a user-defined function block and utilize that instead of doing the sort of logic programming that I've performed. So to make this easy on anyone who's going to be doing analog totalizing in the future, I've created a user-defined function block that allows you just to drop into your application and make that happen without going to all the effort that I went to create this example application. So let's go back to Cscape. And I'm going to go ahead and close this program, my program from scratch. And I'm just going to create a new application. And I'll make it variable-based advanced ladder because that's what we need in order to be able to use user-defined function blocks. I'm going to go ahead here under Logic Modules. I'm going to right-click, hit Import Logic Module. I'll hit star.cpu so that Cscape can find the user-defined function block that I previously created. It's called ALG_TOT. And I did not protect the UDFB, so you can see the logic inside, and you'll notice if we were to study it, you'll notice it's pretty much identical to the logic I've just shown you. But I'm going to go to my main loop now, and I'm going to add a UDFB to my program. But before I do that, I'm going to go into my hardware configuration and make sure that I've created a high-speed counter using internal totalizing of the 10 megahertz clock. So I go to local I/O, XLIO type 2 in this case, go to the high-speed counter setup. For one of these counters, I'm just going to do counter number 1. I'm going to do totalizing, and by default, it's set for internal mode with the internal clock of 10 megahertz. So that's all I have to do to enable that capability in my OCS. And it so turns out that for the accumulator in the first high-speed counter, that is mapped to %AI 401. So that's the analog input register I'll need to be using for my application. So now let's go ahead and add that UDFB to our logic. So I'll go ahead and do an always on contact here, create a new rung, and I'm going to drop in this UDFB. Whenever we drop in a UDFB, we have to give it an instance name. So maybe what we're doing here is we're measuring the volume or the number of gallons of water in our flow application. So I'm going to go ahead and just give this an instance name of gallons of H2O. So that's what I'm naming my function block. Now I'm naming all these variables on the fly. So what do we have here? Well, these are the variables that are inputs to our high-speed counter. the inputs to our UDFB, and these are the outputs from our UDFB. So let me start with an enable. The enable signal, in the case of this user-defined function block, when that's on, totalizing will happen. In other words, we'll keep adding to our total. When that's off, we've prevented the totalizing from incrementing. So that's the whole function of that. I'm just going to create a signal called enable. This is the signal that we need to get from our high-speed counter. That's the 10 megahertz clock. So I'm going to call this HSC 10 megahertz. This is the way that we can clear our totalizer if we ever need to. I'm going to assign a variable called clear push button there. And then this is the analog signal, or the variable that's tied to the analog signal from our flow meter in the case of a liquid flow application. So I'm going to call this flow AI for flow analog in. And then this is the minimum value of my analog input. I'll say 0. I'm not going to do a variable here. I'm going to make it a fixed constant. So min and max is 0 to 32,000. For my engineering units, I'll say it is 0 gallons per minute to 100 gallons per minute. That's my scaling. And of course, these could be variables. They don't have to be constants. And then my output is going to be my accumulated volume of water in my case. So I'm going to go ahead and just name this total gallons of water. And then this is just a simple status of the UDFB. So I'll just call this gallon H2O status. Now, when I hit OK here, it's going to, because I'm creating all these variables on the fly, one by one, Cscape is going to come up and prompt me to fill in all the details on all these variables. So let's start that process now. So I hit OK. It's telling me enable does not exist. Do I want to create the variable? I do. So a Boolean global variable named enable is fine. The next one is the high-speed counter 10 megahertz variable. Do I want to create that? I do. Now, in this case, I need to make sure it's unsigned double integer, which it is, but I also need to map it to that high-speed counter accumulator that's at AI 401. So I'm going to do that right now. It's telling me the clear push button does not exist. Do I want to create this variable? I do. Again, a global Boolean is fine. Flow AI does not exist. Do I want to create this variable? This is the signal from my flow meter. Okay, so this is not unsigned because the data could come back negative depending if it's a little bit below range. So I don't want to make that unsigned. I'll make it an integer. And I'm going to map this to the appropriate analog input. And let's say it's analog input 1 where that flow meter is wired. And then total gallons does not exist. Do you want to create the variable? I do. This is important here. Now, my total gallons of water, I've selected in my UDFB that this is a long real value, not a Boolean, but a long real. So I need to make sure that a long real is selected here. It is, and now I'm done. And then it's asking me for the status variable. I'll make that an integer as well. And global is fine, and we're done. Really, this is all I would need to do in a new application where periodically I'm going to be calculating flow, doing analog totalizing. This is all I have to do in that scenario when I take advantage of a UDFB that's already been created. So again, you can see we stress here on this channel the advantages of UDFBs a lot. And I think you can see in this application how simple it is just to use one that's been pre-created. And even if you decide to create analog totalizing from scratch, it's not quite as bad as it looks. It's really fairly straightforward. That wraps up our demo. Let's go ahead and wrap up our topic for today. Analog totalizers are more challenging to apply and more prone to error than pulse totalizers. Why is that? Well, we have to accurately measure analog, we have to accurately measure time, and then we have to do a bunch of calculations, and we have to keep track of a total. Whereas with a pulse totalizer, we just count pulses and we multiply by a scaling factor. So that's a little bit more straightforward. However, there are certainly applications where you need to do analog totalizing and pulse totalizing is not an option. And one case, of course, being where the sensor you have and that you've been given to use is an analog sensor instead of a pulse sensor. Now, when you're using an OCS as an analog totalizer, you should certainly use a unit that has built-in analog. That's the best approach because then you know your analog readings are going to be synchronized with your time calculations. For most accurate time calculations, take advantage of the built-in 10 megahertz clock that's built into the high-speed counter capability. And then if you have an application like this in the future and you'd rather just use this user-defined function block instead of create your own logic, we're going to post this UDFB online where you can access it and use it anytime you like. So hopefully you got some good out of that particular topic for today. This is the part of the program where I remind you that we're here every Tuesday at 2 o'clock, whether we're fully live like today or whether we are streaming live a pre-recorded video. Next week, what do we have in store for you? Well, I'm going to show you another user-defined function block that I have created that is going to be posted for anybody's use that will allow you to use a drum sequencer in Cscape. So instead of building your own drum sequencer, we're going to show you how to use a pre-built user-defined function block in that function. Now, for those of you who aren't familiar with what drum sequencers are, of course, we'll cover that as well, and you can decide for yourself how useful that could be in your application. So I do want to mention now, if you haven't done so already, please consider subscribing to our channel. It doesn't cost anything, and if you choose notifications when you subscribe, you'll be notified every time we go live or every time we post a new video. Okay, so until next week, when we talk about drum sequencers, I hope everyone continues to have a happy holiday season, and let's all get out there and do us some good until next week.